These slides will address the effects of radiation on your biology. So we will describe biological effects of ionizing radiation, we'll define units of measuring radiation exposure and explain how tools that measure it work, and we'll list common sources of radiation exposure in the United States. Okay, so what are the biological effects of radiation? We don't really worry about non-ionizing radiation. So non-ionizing radiation is not going to produce ions when it hits something. Ionizing radiation has enough energy to damage cells, in particular DNA. So you can break bonds with it, and if it's not repaired, you get bigger problems. So non-ionizing radiation is basically visible light on downward in energy. Ionizing radiation starts at UV. UV mostly has the energy to break double bonds, and it goes up from there. So as you get to X-ray radiation, you're doing more damage, and gamma radiation, you're doing much more damage. But basically, you start to break bonds within chemical compounds. You start creating ions, and those ions can bash things apart because they have higher energy, and it damages your DNA. And all of a sudden, your cells can't reproduce. They can't fix themselves. And so it does some major medical damage. All right, so let's talk about radiation effects. If you have something with a high mass, like an alpha particle, it actually can't go through things that are very thick. So for example, it could be stopped by paper. But on the flip side, alpha particles are highly ionizing because they have a lot of energy due to the fact that they have a lot of mass. If you remember, kinetic energy is 1/2 mass times the velocity squared. So if you've got a pretty fast-moving particle going close to the speed of light, it's going to do more damage than, say, a gamma ray, which is something with no mass. So it has a high ionizing power. Okay, beta particles and positrons can go further. They can get through, say, your skin, but they can't get through a sheet of metal. So they have less penetrating power. So they have more penetrating power than an alpha particle, but less than, say, a neutron or a gamma ray. Neutrons have more energy, and so they penetrate further, but they've got a similar charge to a beta particle, so they're ionizing about the same amount. And then gamma rays don't ionize very much because they don't have a lot of mass, but they do have a lot of energy, so they can penetrate really far through meters of concrete and through lead. Lead being a very dense thing, which is likely to stop stuff. All right, so let's talk about where we get exposed to radiation. So this is a graphic about the relative amounts of radiation that we get on a yearly basis in the United States. So about half of our radiation exposure comes from natural stuff, and half of it comes from medical tests on average. Now, if you haven't had a radioactive tracer put in your body, or you haven't had an X-ray recently, then you actually haven't received as much relative radiation from that source. So most of yours is coming from natural sources. But what does this tell us? We want to avoid unnecessary medical procedures, since 50% of our artificial, actually more than that, more than 50% of your artificial exposure to radiation is from medical procedures. So if you can reduce the amount that you get from a medical procedure by not having a medical procedure, you will overall reduce the amount you are exposed to by unnatural means. Okay, and when I say unnatural means, there are things like when we burned coal, we actually put up some uranium-238 into the atmosphere when we do that, and that is decaying, and we experience radiation from that. Okay. Natural sources of exposure are things like sunlight, right? It has UV rays and cosmic rays, and they're hitting us all the time. We also get hit from our own bodies. We have a certain amount of radioactive isotopes in our body, including carbon-14, that are emitting radiation all the time. In fact, 29 milligrams. We live close to a nuclear power plant, so we get a little bit from that. there's lots of different ways that we receive radiation. But one of the highest that is naturally occurring is radon. So radon is a natural decay product that the rocks under our feet are constantly putting off. Radon is a gas, but it's very dense, so it tends to collect in the basement of homes. So if you want to limit your natural exposure to radiation, you should properly ventilate the lowest floor of your house in order to get radon out into the atmosphere. Okay, so this gives you a good idea, this nice little chart, how much you're being exposed to on an annual basis and why. So let's talk about how we detect radiation. So there's different types of detectors. The most famous one is the Geiger counter, where you ionize a gas and you measure the energy of that ionization. You can also do a scintillation counter, which glows, and then you measure the signal from the light. And then there's various dosimeters, which are badges worn by workers in radioactive environments. And they're about the size of a credit card, although the thickness varies. It depends on the type of detection used in the batch. So you can use a quartz crystal monitor, just literally a piece of quartz that we monitor for certain types of changes due to radioactivity. They can use a scintillation counter. They can use film that reacts to radioactivity. Actually, the way that we found out that radon was a problem in most U.S. homes, somebody who worked at a Pittsburgh nuclear reactor, his badge kept coming back really high positive for radiation. And so they checked the entire building. They're like, nowhere that he's been has this radiation exposure. And it turned out he was taking it home at night and he was getting radon exposure. And so he was getting really high radioactivity from the radon. And as a result, now our codes for residential things include radon. You have to check for radon, and if it's there, you got to vent it out of the house. Anyway, I digress. The unit of radioactive decay, the SI unit, is the becquerel, which is 1 decay per second, which is all nice and good, but in general, we get a lot more than 1 decay per second, so most of the time what you'll see is the curie, which is a CI unit, and it's 3.7 times 10 to the 10th decays per second. This is based off of a more realistic number of decays happening. The unit of radiation dose is the gray, or capital G, lowercase y. It's 1 joule of energy absorbed per kilogram of tissue. So in common use, we use a rad, which is 0.01 joules per kilogram of tissue. And that's closer to what you actually see, which is why we use that unit instead. Okay, so now we know how to measure how much radiation is coming off, but how do we measure how much damage that does? So the unit of measuring damage is the sievert, or the rem, which is the Röntgen equivalent for man, or millirem. 100 millirems is equal to 1 sievert. But that just tells you how much you've absorbed, basically. What you absorb also matters. So the radiation biological effectiveness, or RBE, describes how much damage is actually done by the radiation you were exposed to. So if you look on the right, we have that nice little chart. The activity of our source, how much it's giving off, is measured in becquerel or curie. So that's the number of decays that are happening. And then we have our absorbed dose, which is the joules per kilogram of tissue. But then we also have that biologically effective dose. So we take how much the activity is and we multiply it by what type of damage it can do. So if you have an alpha particle, it's heavier, it does more ionization than, say, a beta particle, so it's a 10. You multiply your activity by 10 for an alpha particle and by 2 for a beta particle because it weighs so much less. And you get the RBE. And then the RBE times the absorbed dose is the amount of damage you do. So let's try some calculations. Let's say we have cobalt-60 with a half-life of 5.26 years, and it's used in cancer therapy. A 2.5 gram sample of cobalt-60 is available for cancer treatment. So what is the activity of cobalt in becquerels, and what is the activity in curie? So In order to figure this out, we first have to say what is the half-life of this thing. So we need to find a radio decay constant. So we're going to do that first. So activity is going to be equal to the radio decay constant times the amount of stuff you have. So we put in our variables, the 0.693, which is what natural log of 2 is, divided by 5.26 years times the amount of stuff we start with, which is 2.5 grams. We get 0.475 grams per year are decaying. But the becquerel is in seconds. So we need to convert years to seconds. So we get 1.51 times 10 to the negative 8th grams per second. But wait, the becquerel is in decays per second. So how do we figure out how many molecules are decaying for each second? We are going to use moles and then Avogadro's number. So we convert to moles, and then we convert to the number of atoms that are decaying, and we get 1 decay per atom. Okay, and so then we find 1.51 times 10 to the 14th decays per second, which is the same as a becquerel. All right, so now we want to convert to curies. We have a relationship between the number of becquerels and curie, and we use it. And we find that we have 409 curies of radiation that we will be exposing this poor cancer patient to in order to hopefully cure them of cancer. So, oh, the fun of radiotherapy. All right, so now we can do some calculations with basically how much radiation we're getting. We're not going to get into doing the exact dosages because we don't have time. We're already at 40 minutes for the presentation. All right, which brings us to the health effects of these things. So with low exposures, we have relatively small problems. So we might have a small change in blood chemistry, you might be nauseous, you might have fatigue or vomiting. And as you go up in dose, you start to have bigger problems, which are much more of an issue to your long-term health. So by the time you hit an exposure of 100 millirems, you can start causing major hemorrhaging in your body. If you get up to 400 millirems of damage or of exposure, you could die within 2 months of that exposure. So if you look up Alexei Navalny, you can see exactly how that works out. He was poisoned by the KGB, and he died like 2 months after his exposure. It was not pretty. Okay, you get 1,000 millirems of exposure. It completely destroys your intestinal lining. It causes internal bleeding and death within 1 or 2 weeks. So as you up the exposure, you up the chance of death. The people who were doing the emergency work and putting out the fire at Chernobyl, the reason why they died within like days to weeks is because they got 1,000 to 2,000 millirems of exposure. And part of how we know that this is what happens to you is because of their deaths. Part of how we know how lesser exposures hit you and how they cause problems is by tracking people who worked in the what do they call it? They were clocks, basically, where they coated the dial with radium, and you could see it at night. It would glow because it was radioactive. But the people who were painting them would literally lick the radioactive paint and eat it. And so we could track exactly what happened with exposure by happening to track what happened with their health. So, a lot of the history of how we found out about this stuff is not pretty. We'll leave it at that. Anyway, I will see you guys in class. I'm sorry that this was so long. I didn't realize how much I was going to try to cover here. Most of this is information that's just kind of cool to have, but you won't actually be tested on. Know how to do the calculations, know how to do your radioactive decays and stuff, and the questions that I put on the problem set for today are closer to what you might see on a test. But I couldn't resist it. It's just cool information. I will see you tomorrow. To summarize, ionizing radiation has enough energy to damage cells, especially DNA, which is why it causes the cancer. Alpha radiation is highly ionizing, but it has a very small penetration depth. In other words, paper works to stop it. Beta radiation is a mid-range ionizer and has a penetration depth that can be stopped by thin metal. Gamma radiation is weakly ionizing, but it has a large penetration depth, as in feet of metal or concrete. So you might think that your biggest problem is maybe alpha radiation because it's super ionizing, but actually it's probably gamma radiation because you really can't avoid it. Most natural sources of exposure come from radon gas, followed by the sun. Non-natural exposure tends to happen via medical diagnostic tests. A unit of radioactive decay is a becquerel, which is 1 decay per second. Or it can be measured with a Curie, which is 3.7 times 10 to the 10th per second. The unit of radiation dose is the gray, which is 1 joule of energy absorbed per kilogram of tissue. In common use, you might see the rad, which is 0.01 joules per kilogram of tissue. The unit of measuring energy of damage is the sievert, or Röntgen equivalent for man, MREM. 100 millirems is equal to 1 sievert. And the radiation biological effectiveness, or RBE, describes how much damage has been done. Health effects of radiation exposure can range from nausea all the way to death.